next topic is about co-registration and realistic head modeling. The first question is why should we perform a co-registration of our electrodes with an individual brain? Well, the two differences are shown here. So with co-registration, I will be able to get to a display in my anatomy. Without co-registration, I will have my sources in an approximation of the brain or in just a head scheme like the one shown here. And the other big difference is that with co-registration, I can work with internal landmarks. Or if I look at the situation without co-registration, my reference points will usually be the nasion, the left preauricular point, and the right preauricular point, the so-called PAN coordinate system for preauricular and nasion. And this is an external reference system, so we don't know exactly how the brain is located with respect to these coordinates, so there's always some scope for error there. And if I go to an internal landmark system, so if I perform a co-registration, I can work with the coordinate system that's based on internal landmarks like the anterior commissure and the posterior commissure, ACPC. And this should give us a more precise representation of the source locations in the brain. And one of our members of BESA did a study on this by looking at the spread of auditory heterogyrous localization over different subjects using the external and the internal coordinate system. And if I look at the mean position and the distance to this mean point in the left and right hemisphere, then there was a significant difference using the external coordinates, so the preauricular point and nasion, compared to a co-registered coordinate system using the AC and PC points. In both cases, left and right hemisphere, I then get a sort of smaller spread of these points. So co-registration is essential when I want to look at source localizations, either to compare them between two groups of subjects, or for example, if I want to compare source localizations at two different time points, two different measurements that I make, for example, before treatment and after treatment, and so on. Then the next thing we can do is we can also use a realistic head model, and this should further improve our localization, because we can then use the individual anatomy of the subject for calculating the forward model. Of course, when my precise positioning of the source is the leading research question, then this is an important thing. Or when I work with medical cases, for example, to localize epilepsy data, epilepsy activity, then I really need the best head model I can get. Also, if I want to look at which brain region is involved in a particular cognitive task and I want to compare this, then it makes sense to use realistic head models. So how do we get to these models? The first thing is that we generate a realistic volume conductor, and we do this using the so-called finite element method, or finite element modeling, FEM. And this results in our implementation in 4 different compartments that the brain is subdivided into. The first one is the brain itself. So we can see this red shape here, that's the brain. Then we have the cerebral spinal fluid in blue, the skull in green, and the scalp in orange. So these 4 compartments are automatically segmented in BESA MRI, and for these compartments then the current can be calculated how it propagates through the different compartments, and then to calculate what signal is generated on the sensors that we measure. Why do we include the cerebral spinal fluid? The reason is that it has a different conductivity compared to the other 3 compartments, and so the current flowing through the volume will be deterred by this CSF layer. Here we have a study showing what the effect is of not using the CSF or using the CSF. So the error if I don't use the CSF is shown at the top, and you can see especially in the frontal, prefrontal parts and also in the inferior part of the cortex, I can so here and here I can really see a large effect up to 8 millimeters in localization error. And if I do use the CSF, then this localization error is much smaller. Yeah, and once I have got my volume conductor, then I can calculate the lead field, and this is part of the co-registration. So the lead field is calculated for a grid of sources in the brain to calculate their contributions on the electrodes or MEG sensors outside of the brain. Again, so co-registration makes sense when I want to check on source localizations between different groups. Individual volume conductor is always important when source localization is the key aspect of my research. Okay, I'm going to now show a little bit how that works. So I'm going to work with a different data set now, because this is a grand average, and grand averages don't lend themselves to co-registration. So I'm going to work with an individual recording of one subject. Just going to go to the examples folder and open. This is also an auditory experiment where two different stimuli were presented, a target stimulus and a standard stimulus, and the subject responded to the standard stimulus by hitting a button. So again, we're looking at localization of the auditory areas. So to do this, we want to perform a co-registration. First of all, let me check on the channel configuration. So there's this file, head, surface points, and sensors, load coordinate files section, or shortcut Control L. It's easier. And I can see that I've got 65 channels, including my reference, and I've got a digitization of my head surface points with 68 locations. So I've got my 65 electrodes plus the 3 fiducials. They were all digitized, so I can use these for the co-registration. I'm going to cancel this and now go to File, MRI Co-registration. And if I do this, and BESA notice that I do not have a co-registration yet, then automatically it asks me to save these digitized coordinates as a so-called SFH file, surface head points file. So I'm just going to save this now, and then automatically the BESA MRI software is started. And yeah, I accept this, and now I can go through workflow to co-register my data. So the BESA MRI screen is subdivided into 3 areas. On the right-hand side, I can interact with the workflow. In the center, I can see the results of my actions, and on the left, I get the overview of where I am in my workflow. So now I'm going to start a new co-registration. And the first thing I need to do is to tell BESA MRI what I want. So I want to generate a FEM EEG lead field, and then I can see the steps of this workflow on the left-hand side. So go next. Yeah, what I need to do now is tell BESA MRI what my MRI project is. So the first thing I did previously was to perform a segmentation of the MRI data set, and this is now loaded. And yeah, I did a previous co-registration, so I have already marked the 3 fiducials in this data set. I can take this out, and I can redo this marking if I want to. So I can set the position of the nasion. I can set the position of the left preauricular point. This should be in line with how I recorded them during the digitization of my electrode cloud. and similar to the right preauricular point. So now I've set my 3 points, and I can go next. And the next thing to do is to load that file that I've just written from the BESA research. So select the co-registration file. If I go to date modified, then this one that was just written a minute ago is the one that I want. And it's automatically loaded, and I can see as an initial fit is performed using the fiducial positions, and I can already see a pretty good match of these purple fiducials which I recorded in my digitization, and the blue fiducials which I pointed out on the skin surface myself. But I can also see that some of the electrodes are not perfectly aligned with the head shape, so I'm going to go with the next step, which is performing an automated fit of the electrode positions, and now I can see it's a better fit. It's got 2.3 millimeters mean distance error, and one electrode is a bit off because it's simply the neck electrode, which is not part of the MRI anymore. So I can still manually improve this a little bit by, for example, translating in Y direction until I can see all the electrodes. And yeah, when I'm done with my corrections, then I can press the next button or simply the space bar to move to the next step. And the next step is now to compute the finite element model for these 65 electrodes. And I can here also adjust the conductivities. So if I want to work with a child, for example, I've got different conductivity ratios than with an adult, but by default I work with an adult value, and that's what I'm going to keep. Yeah. So the next thing is now calculating this FEM, and in fact it's going to take about 20 minutes, so I'm not going to go through with it. I just wanted to show you how this works, and I'm just going to stay here long enough to show you how long the computation of one electrode will take, to give you an idea, and then we are going to work with a pre-computed result. So the first few seconds are the initialization of that finite element model calculator, and then it starts by computing the lead field for the first sensor, and thus this takes between 20 and 30 seconds usually, and then it moves to the next one. So yeah, now it's already done the first one, and it goes to the second one. So this is about the speed that it has, so it'll take about maybe 15, maximum 20 minutes for this 64 electrode cloud. So I'm going to cancel this and instead go back to BESA and use my pre-computed file, which I had saved earlier. So it's this one here, and once I completed this co-registration, then I can see the result in this co-registration dialog. So I can see entries for the MRI, for the head surface, for the brain surface, and I get information that here I've got an individual FEM defined. This is good, and now I'm going to try and use this individual head model for localizing my auditory activity. So drag over this first segment with the target stimulus and click source analysis. And here I now need to define the precise interval I want to work with. So I'm going to deal with 100 to 300, minus 100 to 300. And the filters as shown here. Excuse me. Yeah, and now I see my window again. And let's have a look at the PCA. So if I drag from about 80 to 110 milliseconds, I should get a good, so almost 99% in the first PCA component. I'm going to add a regional source and another one, and then press all fit, start fit. And I'm also going to add a symmetry constraint for this regional source, and this is the result I get. And now I have not adjusted the head model yet, so this is the result for the 4-shell ellipsoidal head model, as it says here at the top. And let's see where we end up with the anatomy. So if I press the A key for anatomy, then I can see where they are. And I can see that they are a little bit too frontal and a little bit too high compared to the actual location of the auditory cortex. So see this, can you see my mouse? This is where the Heschel gyrus is. This is where my source came out. So this is the result I got from the spherical head model. And now I want to compare it with the result for the finite element model. So let me switch these, let me close this, switch off these two sources, and instead use two new sources and change the model. And now I can use this combo box up here at the top to change my head model from 4-shell ellipsoidal to individual FEM. And again, I'm going to use a symmetry constraint, so make this source symmetric to the regional source 3, and now fit these two sources over the same interval, just with the individual realistic head model. And I can already see in the head schemes that they turned out more inferior and also more posterior than the first two sources that I entered. So I'm curious to see what that looks like in the anatomy. So in the anatomy, I can now see the first source is really exactly on the Heschel gyrus, and the other one is a little bit interior, but otherwise it's also in the absolutely correct position. So so the individual FEM model has significantly improved my fit localization by maybe about a centimeter or so to get my solution into the right position. Yeah, so especially for more inferior sources, the finite element model, and also for anterior sources, it gives you a much better result. If you work with somatosensory or more posterior sources, usually the spherical model is not bad. But yeah, for the more deeper sources, it really the individual FEM brings you a much better localization.